Welcome to my first Fourier Series exam. I'm going to do this as quick as possible. So Fourier Series is basically if you have a function that's in a square wave or any other weird function, you use sines and coses to represent that function with an infinite number of them. Now the goal in Fourier Series is simple. Find a0, an, and bn. So it's just three coefficients and then you find out your final f of x. Now, what we're going to do in this example is really simple. And this is how these are the formulas. So a0 is the formula for finding a0 there, obviously. And there's the formula for an. And there's the formula for bn. Now, there's different conventions for Fourier series. I'm just going to show you my way of doing it. I've learnt two ways. And they all mean the same thing. They all get you a final answer that's the same in the end. Some are easier than others, and I find this way to be personally, in my opinion, a lot easier to solve Fourier series. Now, what do we do? Do we have a problem? So let's just say we have a piecewise function, f of x, which is equal to 0 when 0 is less than x is less than 1, and minus 1 when 0 is less than x is less than 5 or something. Who knows? It doesn't matter. So we have this function. So what do we do? What should we do? Well, I just stuttered a lot, but we're going to graph it. We're going to graph it. We know it's open-ended because it's just like that. So it's 1. And then it goes to minus 1 when 1 is from 0, not 0, sorry, 1 to 5. So let's just say that here is 5. By the way, not to scale, obviously. Now, sorry, that came off the page. So what am I going to do now? Well, in a normal Fourier series problem, I'd find a0, an, and bn. But I'm going to show you a neat little trick, which is unique and beautiful to Fourier series. What I can do, well, it's probably not unique, but I'm just talking out of my butt there. But anyway, what I can do is I can pretend that this is a sine function or a cosine function. So for it to be a sine function, it would be like that. Cosine function will be like that. You just extend the graph, right? And we know, and the reason why is because the sine function is odd, so we would extend this function in an odd way, and a cosine function is even, so you would extend that function in an even fashion. So I'm just going to choose to do a Fourier sine series, which means I am going to pretend, just for a short little while, that this function is odd. So I'm going to do a Fourier sine series, which means, well, from 0 to 1, that doesn't change. But it's going to go to minus 1, right? From 0 to 1. Now, from 1 to 5, instead of minus 1, it's going to go to plus 1. And then it's going to be like that. As such. Now, I forgot to mention what t was. So t is the period of the function. And in this case, t equals 10 because t goes from minus 5 to 5. So that's that. So since we're doing a Fourier sine series, by the way, we don't need a0. a0 actually becomes 0 because the average over the entire function should equal 0. So that's just a side note. If you do an, i.e. a cosine series, Fourier cosine series, you would have to find an. But in the Fourier sine series, you don't. You don't need it. So that's just a good little tip, so you don't waste your time finding out that a0 equals 0. So let's get into the problem. So we're finding out bn since we're doing a Fourier sine series. So the formula, what's the formula for bn? Well, it's 2 over t times the integral from a to b of f of x sine 2n pi x over t dx. All right, I was talking really, really fast then. So 2 over t, what's t? 10, so that's 1 over 5 times the integral from minus 5 to 5 of f of x, because I haven't split up the function yet into its piecewise constituents, sine 2n pi x on t. Well, t is 10, so that's just n pi x on 5 dx. So so it's 1 over 5, 1 over 5. It's the same, right? But here's the difference. I'm going to pretend, well, I'm not pretending anymore. Now I'm going back to the original problem. How do I do that? I halve the limit of integration. So the limit of integration is from minus 5 to 5. Now I'm going to make it from 0 to 5. So I'm going back to the original problem, basically. But when I halve the limit of integration, I have to bring a 2 out the front of the integral. I'll show you. So it now becomes 2 out over 5 times the integral from 0 to 5 of f of x sine n pi x on 5 dx. Real simple, right? It's not that hard. It's really not that hard. So these are just rules and things you've learnt along the way in your journey of calculus and blah, blah, blah. All right, so we have 2 over 5 now. Now, because I know that it's the value of f of x is 0 from 0 to 1, I just ignore that piecewise part because it's just a waste of paper space and we don't want to be killing trees, you know. So, even though I've probably killed millions of trees with the amount of practice I've done, like seriously, but it doesn't matter. Anyway, so bn is now 2 over 5 times the integral from 1 to 5, since I'm ignoring the 0, of minus 1 sine n pi x on 5 dx. Okay, we're almost there. We're on the home stretch. So now it just becomes negative 2 over 5. Now what's the integral of sine? Well, we know that the derivative of sine is cos. So if we're integrating sine, that means we're going to a negative cos. So it's going to be negative 5 cos n pi x on 5 all over n pi from 1 to 5. And why is that true? I'll just quickly end this video before I evaluating this integral and finding the final answer, which means I am splitting this video into 2 parts. So I want to show you just how I get this answer here. And it's really simple. It's just a u substitution. So let's say I have the integral, right, of sine n pi x on 5 dx. Well, I'll let u equal the inside, which is just n pi x on 5. du is equal to n pi on 5 dx. And if we take it all to the other side, it becomes 5 over n pi du is equal to dx. So then when I plug that in, and voila, integral of sine u is negative cos u, negative cos 5 over n pi. So that's your final. That's how I get this answer here. So some people find this step confusing, but it's really as simple as a u substitution. So thanks for watching, and I'll finish off the problem in the next video, and I have many Fourier series videos to come because I've done it that many times that I can do it while I sleep. Anyway, see ya.